Good morning, Professor Stone, Professor Evans, Professor Young, Professor Jargovsky, ladies and gentlemen. Welcome to the Shaw Prize Lecture on Astronomy, where we celebrate and pay tribute to the pinnacle of academia through a tradition that rewards pioneers with not only vision, but also intellect and persistence. We are very delighted to have all of you today at this meaningful event. My name is Christy, a first-year student in the Faculty of Science. It is our great honor to have Professor Edward Stone, Shaw Laureate in Astronomy 2019 with us today. Professor Stone made tremendous contribution in leading the Voyager Project over the past 4 decades, which transformed our understanding of the 4 giant planets and the outer solar system. The Shaw Prize, established under the auspices of Sir Run Shaw in 2002, is an international award to honor individuals who are currently active in their respective fields and have recently achieved distinguished and significant advances. The award is dedicated to furthering social progress, enhancing quality of life, and enriching humanity's spiritual civilization. May I now invite Professor Matthew Evans, the Dean of Science of the University of Hong Kong, to give a welcoming address and introduce our speaker. Professor Evans, please.
Good morning, Professor Stone, Professor Young, Professor Djokovic, ladies and gentlemen. Welcome once again to the Shaw Prize Lecture in Astronomy 2019, which is entitled Voyager, Journey to the Giant Planets and Interstellar Space. I'm Matthew Evans, and the Dean of Science of the University of Hong Kong. It's our great honour to have Professor Edward Stone, Shaw Prize Laureate in Astronomy 2019, here today to talk about his work in astronomy, including the well-known Voyager Project. Professor Stone's leadership in this project over the past 4 decades has transformed our understanding of the 4 giant planets, Jupiter, Saturn, Uranus and Neptune, as well as the outer solar system, and has now begun to explore interstellar space. The Voyager Project consists of 2 spacecraft launched by NASA in August and September 1977 to explore the outer solar system. Both spacecraft flew past Jupiter and Saturn between 1979 and 1981, and Voyager 2 also visited Uranus in 1986 and Neptune in 1989. For the foreseeable future, Voyager 2 will remain the only spacecraft to have visited Uranus and Neptune. The unique data generated by these missions are particularly important for our study of exoplanets, because it turns out that Uranus and Neptune appear to be more representative of the bulk of exoplanets that we're finding than do the inner rocky planets of the solar system. Although many scientists, of course, have been involved and have devoted their careers to the Voyager project, the dominant figure in this mission has been Professor Stone. He has served as the project scientist from 1972 to the present day, and is in charge of the spacecraft's 11 instruments. During the planetary flybys, he became internationally known as the public spokesperson for Voyager and explained Voyager's scientific discoveries to the public with remarkable lucidity and scientific authority. Professor Stone is currently the David Morris Rowe Professor of Physics and the Vice Provost for Special Projects at the California Institute of Technology, USA. He earned his PhD in physics from the University of Chicago in 1964, and since the Voyager spacecraft launched in 1977, Professor Stone has led and coordinated 11 instrument teams on this project. He has also served as the director of the Jet Propulsion Laboratory from 1991 to 2001, overseeing many space-based missions, including Cassini, which sent back data and images from Saturn between 2004 and 2010, and a program of Mars exploration, including Mars Pathfinder and its Sojourner rover, which was the first rover to operate outside of the Earth and the Moon. In the mid-1980s through to the 1990s, he served as vice chair and chair of the board of directors of the California Association for Research in Astronomy, which is responsible for building and operating the Keck telescopes in Hawaii. He is currently playing a similar role in the development of the planned 30-meter telescope, an international partnership that includes the US, Canada, China, Japan, and India. Professor Stone is the recipient of numerous awards, including the President's National Medal of Science in 1991, the Magellanic Premium 1992, the Carl Sagan Memorial Award in 1999, the Philip J. Klass Award for Lifetime Achievement in 2007, the NASA Distinguished Public Service Medal in 2013, the Howard Hughes Memorial Award in 2014, as well as all of those things, he finds time to be a member of the National Academy of Sciences. So without further ado, in recognition that you haven't come to listen to me, you've come to listen to Professor Stone, I will pass the floor over to Professor Stone. Professor Stone, please.
Well, thank you very much. It's all right. Okay. Well, it's my pleasure to be here and talk about the Voyager mission, which really got its start back in 1972 when we were first started building the equipment, and today we're still tracking it. And I'll be reporting on some of the discoveries that the mission has made over the last more than 40 years. Have I got, all right, that's okay. This is really a journey to the outer planets and beyond. The outer planets are giants. The rocky inner planets like the Earth are quite different than the giant gaseous planets and gases and liquid bodies, and you see the size scale is also quite dramatically different. There is so we're seeing much more about the giant planets from the Voyager mission. I'll talk a bit about that, and then what's beyond, which is interstellar space. So this is the opportunity we had. That is, every 176 years, Jupiter, Saturn, Uranus, and Neptune are arrayed in the sky in such a way that a spacecraft can fly by all four in sequence, of course. I hope you can see the red dot. They were both launched in 1977. Voyager 2 was launched first, but it was slower, so Voyager 1 caught up with it and became the first encounter with Jupiter back in 1979, followed by Voyager 2, and Voyager 1 went on to Saturn, which is, and then swung up out of the plane of the planets, headed toward interstellar space. Voyager 2 stayed in the plane of the planets from Jupiter, Saturn, Uranus, and finally Neptune, when it swung over the North Pole of Neptune and headed downward. So we had Voyager 1 heading upward out of the plane of the planets, and Voyager 2 heading downward. And over a period of from launch in 1977 to the last encounter with the planet, which was 1989. So that's the journey that I'm going to be talking about, and what happened after the 1989 was the mission to interstellar space, which I'll be describing what we learned already from this journey to interstellar space. This is the spacecraft. The big antenna that you see is about 3.6 meters in diameter, and it always points at Earth. That's the way it reports data back to Earth. So this particular axis of the spacecraft always points at the receivers on Earth. And as I say, this is 3.6 meters. And we have science instruments on the long extended boom. These are the magnetometers measuring the magnetic field of the planets and the magnetic field of interstellar space. Here is the power supply, the radioisotope thermoelectric generators. Radioactive decay creates heat, which is converted into electricity to power all the instruments on the spacecraft. We have two big antennas, long antennas, which record radio waves and plasma waves in the environment and of the planets as well as interstellar space. So that's the spacecraft. There were two of them, launched in 1977. On this journey, we had two because it took 4 years to get to Saturn. And in those days, spacecraft weren't all that reliable, so we had two just in case only one made it all the way to Saturn. Turned out both are still functioning today. many decades later, which is fortunate because that's how large the extended solar system is that I'll be talking about today. First, the big giant planets. These are much different than Earth. I did show you a photo of the 4 giant planets, and for scale, there was a small Earth that was there. This is the Great Red Spot. The Great Red Spot, which as you can see here, it's a huge storm system, but it's only the largest of literally many storms. Even the smaller ones on here, the Great Red Spot's about 3 Earths across. So you can see it's a pretty big storm. This is another storm, which is not quite that large. Here's still another one. There's a whole string of storms which develop in this dynamic planet, which we studied with the flyby missions of the spacecraft. There are 2 moons which I'll comment more on. One is Io. It's reddish color. It's right in front of the Great Red Spot, but it's in orbit around the planet. It's not really near it. It orbits past. Just the photographs happen to be, it was in front of the Great Red Spot. And Europa, about the same size, but you can see quite different in character. Just one is reddish color, and the other is a nice snowy white. There's Io. And this is, when we first saw this, we had no idea what we were looking at. It was a real puzzle. But as the flyby continued, we finally realized what we were seeing. We were seeing a planet with 10 times the volcanic activity of here on Earth in this small moon, which is basically the size of our moon. It's the scale. In other words, it's small compared to the size of Jupiter itself. And all the black spots you see are hot lava lakes. And so this is a very active moon being heated by tidal flexing of its crust as it orbits Jupiter. So this is very active, volcanically very active, much more active than the Earth, even though the Earth is much larger. This is the other moon. This is in Europa. Notice how different it looks. It's covered with water ice. It also has this same heating source, but it's further from the planet, so it doesn't get hot enough to melt all the ice. So we have an ice-covered ocean, and we know that from subsequent data that there's indeed an ocean beneath this icy surface that you see. You can see it's cracked from the flexing, from a pull on the crust as Europa orbits Jupiter. What you're seeing is water ice. And we now know that, in fact, there is liquid water beneath that, so there's a massive global ocean on this moon of Europa, and is a subject of further study in the years ahead. This is what it looks like close up, Europa. You notice you can see blocks of ice where you can see the pattern, one ice pattern that's been broken up into smaller pieces as the surface flexes and cracks and then refreezes. One of the questions, of course, is exactly how thick this ice is, and are there spots where the liquid, which is water, which is below the ice, erupts onto the surface and can be studied. That's what subsequent mission Galileo managed to study because it was in orbit. Voyager just flew by and revealed the complexity of this icy surface. So this is just water ice you're seeing broken up and refreezing into this pattern that is quite complex. Then there's Saturn, twice as far from the sun as Jupiter. Jupiter's 5 times as far from the sun as the Earth. Saturn's about 10 times as far. And the most distinctive thing about Saturn are the rings, which are mainly water ice, ranging from tiny BB-sized up to a few which are 10 to 20 meters in size. But they're mostly smaller particles which reflect the sunlight, and you can see some faint features that you might be able to spot right here. Here's a narrow ring, which is a complete ring outside of the broad, bright rings you can see from Earth. So this is a very complex interaction of snowy, icy particles forming the ring pattern you see, orbiting Saturn, and the narrow rings are where moons have kept the material together rather than letting it spread out into the classic ring systems that we're familiar with. There's a major moon of Titan. Titan is almost as large as the planet Mercury. And you can say, what's wrong with this picture? You can't see anything on the surface. That's because there's a very thick smog layer in the atmosphere. The atmosphere of Titan is nitrogen, just like the atmosphere on Earth. But unlike Earth, this does not have any water in the atmosphere. What it has is some methane and other complex organic materials which you can see. So there's a very thick haze that you can't see through in the optical. And it was subsequent missions, such as Galileo, which reported on this is the Cassini spacecraft. The Cassini flew by it went into orbit around Saturn, so it could actually look. This is now a moon this is the moon looks like at Saturn, and you can see as we look more closely the fact there is a liquid on the surface. And this is Cassini data, and there are lakes, actually, these are lakes of liquid methane, which is created in the atmosphere and rains down on the surface. And so this is a very wild terrain, very cold, and water ice is really frozen quite hard. What you're seeing are some more complex organic materials forming the lakes of Titan. This is another small moon of Saturn. What you're seeing here is water ice, but notice up above, there's lots of impact craters. This is an older surface because there have been lots of impacts leaving these craters behind. By the way, this is only about 300 miles across, so it's a tiny world, but look how complex it is. And then there are regions where, in fact, they're absent of any impact craters, which means that, in fact, it's fairly young. This is an old surface. It's been heavily impacted by many impacts over the billions of years. This is constantly being recoded with water ice. What you're seeing is water ice with large cracks from the flexing in the gravitational field of Saturn. And if we take a view from an angle, you can see that, in fact, the Enceladus is a small moon of Saturn, which was seen by the Cassini spacecraft. And you can see the erupting volcanoes, where the heat is melting the water ice, which is in the moon, creating these large plumes of material coming from the surface. So this is a moon that's being melted on the inside and evaporating through those cracks that you saw. The large features you see are the place where the water is erupting through the icy surface, and it's down in this region right here where most of the plumes are active today. So this is a very active surface of an icy moon. So this outer solar system is not a dead system. It's quite alive, and that was one of the major discoveries, was how much activity there is, even though it's quite cold and far out from the sun. There's an example of what some of the plumes look like erupting from the surface of Enceladus, as seen by the Cassini mission in the last 10 years. It's a very, very active place. Then on to Uranus. Uranus is the Earth's at 1 astronomical unit from the sun. Saturn's at 10 astronomical units. Uranus is 19, almost twice as far out, twice the diameter of Saturn. And it's another thing you can't easily tell, since you don't see much in the surface. That's because the cloud layer is very uniform, very much uniform. If you look carefully, you may see a suggestion that if you notice that the pole of this seems to be, there's a brighter area here, and the magnetic pole of this moon. The moon is tipped on its, the planet is tipped on its side, This was pointing toward the sun at the time Voyager visited back in 1986. And you can see that there's a polar cap of, this is all gaseous atmosphere, no solid surface that we can see on Uranus itself. It's the pole of Uranus is right about there. So there's this polar cap of material which you can see in these images. But right now it's very featureless. And the challenge is that the Uranus its year, if you like, for its orbit around Saturn is 84 Earth years. So that right now it's had a long phase of sunlight on the pole. Now, more recently, as it orbited Saturn, the sunlight started illuminating the equatorial region, which is down here. Now, one of the most interesting things at Uranus was the fact that the magnetic field was, here on Earth, the magnetic field is oriented so the pole of the magnetic field is north. And so that's the reason the compass points north. In this planet, the magnetic field is near the equator. And so it makes a very complex magnetic field as Uranus rotates about the axis, which is here is the polar axis, rotates, and that does create a different kind of magnetic field configuration than we have seen in the inner solar system. The fact that the magnetic pole is not at the rotational pole of the planet. One of the moons which we saw was Miranda, and you can notice the check mark, like a class, something you see in class. You can see these things are all ruptures in the icy surface. This is a set of plateaus. Each of the dark streaks you see is an offset, so the surface is very strongly distorted by some early event in Miranda's lifetime. It's currently not an active body, so that is, the surface is not changing any longer. But there was a time period where it was quite active, and if you look down here, you'll see a cliff, and that cliff shows up very nicely here, where you can see this cliff, which is kilometers high on that surface, which has really disrupted the surface of Miranda dramatically. This was mainly a water ice, which you see, but it's no longer active in the sense it's not changing, and at least it has not changed during the time the most recent time. Then it's on to Neptune. Neptune's 30 times as far from the sun as the Earth. So it's really cold out there, and yet we still see activity in the atmosphere. The interesting things is this great dark spot. Pluto has the great red spot, it's called. This is a great dark spot because it just looks dark. Unlike the great red spot, which has been around hundreds of years, this no longer exists. This happened during a very brief period of time, just in time for our encounter back in 1989, and it's probably missing today. So this is a transition, just a transient feature, as are these other clouds that you see. So this is a very cold place, yet even in a very cold place, the atmosphere continues to have a weather system, which is quite interesting. This great dark spot has since disappeared, and time will tell if it returns. This is a moon of Neptune, a small moon, and there are several interesting features that we've discovered on this moon. Notice up here this sort of cantaloupe terrain, which has this surface. This is water ice that's frozen. You can see streaks which are faults in the ice. And in some regions, you can see there aren't any features at all. It's featureless. And then there's this region, the wider region here, which is like a polar cap of frozen frozen nitrogen, not frozen water ice, which is what most of Triton is, but actually frozen nitrogen. And the really remarkable thing is this body is very cold. It's only 38 degrees above absolute zero. And so water ice is frozen hard. But notice there's some dark streaks which are here. A number of dark streaks. We now know that those, in fact, are plumes of stuff erupting from the surface of Triton and depositing stuff on the surface. And we actually saw two of these streaks, which are plumes of some material which is erupted from the surface of Triton. And the wind has carried them. It's a very faint density of the atmosphere. It's hardly measurable, but you can see it did carry the material erupting from the surface and form this long track, which then deposits these linear features on the icy polar cap. So this is a very dynamic moon. You might say, why is there any activity at all at such low temperatures? And that's one of the challenges that one has, is an understanding the mechanism that causes these erupting plumes. But it's a very active planet. There's still a geologic life left for Triton. It's in an orbit which is backward with respect to the direction everything orbits the outer planet. The moons are all orbiting in the same direction around their planet, except this one is in the opposite direction. It's a captured object, in other words. So there are the four giant planets. These are not to scale, but it just shows that, in fact, what Voyager discovered was this is a Voyager image showing all these storm systems, starting with the Great Red Spot and going down to the smaller ones, which are still huge by Earth standards. Then there's Saturn with its rings. And this is Uranus, which had really no visible features at the time we were there because of the season and the fact that the solar wind was hitting the polar region of the moon. And then here was Neptune with its great dark spot, which has since disappeared and not reappeared. There's some other storms you can see. So it's interesting that the temperature at Neptune is almost high, such that, in fact, we can get supersonic winds in the atmosphere of Neptune, and it's quite cold. So these really changed our view of the solar system and the bodies in the solar system, because the inner planets are like Earth. They're solid material. Mercury, Venus, Earth, and Mars are all solid, rocky bodies. It's very much like the Earth, while these are massive bodies of gas. And the temperatures are much colder as well, so that these are dynamically are giant planets and have a different kind of evolution, and much more gas was accumulated during their formation to provide these massive atmospheres, which have complex weather systems and which are, as you can see, vary a great deal from planet to planet. Oh yes. Okay, let me go back a minute. So Voyager basically really changed our view of the giant outer planets. You can see that these are, compared to the size of the Earth, which is not to scale here, I showed that in the earlier slide. These are giant planets. These two are somewhat larger than Uranus and Neptune, but they are giant planets, mainly gas and liquid, deeper in where the pressure is higher. Interesting thing we did when we were leaving Neptune and heading toward interstellar space was to look back at the solar system. And what we saw, you see that little white dot? That's Earth. And it's barely resolved. It's quite, so we have progressed from here out of the solar system into interstellar space. Here are the instruments which are running on Voyager. The Voyagers, now that they're outside, we don't use the cameras anymore. We're not close to any bodies anymore. So we have only 5 kinds of instruments which are telling us what's out there. And I won't read those to you. Just the main message is that this is the kind of information we've gained as we've left all the planets behind and are moving outward in the solar system. And what are we headed toward? So if we start with the moon, and let's see if I can get this. You can see this is the sun. You can see dark spots. These are active solar eruptions on the sun. You can see that there's an 11-year cycle. This is real data, that as the sun becomes more active, there are more spots. That's the way the sun reverses its magnetic field, is with these sunspots, which eventually can carry the magnetic field of one polarity away, and the new polarity erupts. So the North Pole becomes the South Pole, and the South Pole becomes the North Pole. So this is the see, I can go to the next slide. And here's another view of what the sun looks like, which we're now moving away from beyond all the planets. This is the image is actually an image by the SOHO spacecraft of the size of the Earth is that circle. And it's blocked from view by the brighter sun, which is behind it. So we didn't want to see the sun. What we want to look at is the reflected sunlight off of the streaming of the atmosphere of the sun outward into the solar system. And if I can get that to go, there we go. There's a comet. The comet, it's like a weather vane. It tells you the wind is coming from the sun, blowing outward. There was a big eruption on the sun, and we have data like this, which tells us that the outward streaming of the solar atmosphere is very faint. You can see it only if you hide the sun itself from the camera, and then you can see the outward streaming. Could we make it move again, just so you can see the same thing again? And you can see occasionally there's a big eruption. Bam, like that. And that is what it carries, which inflates the magnetic field as it moves outward, forming a huge bubble around the Earth, which is much, much larger than the sun, much, much larger than a planet, but it's in fact a bubble around all of the planets called the heliosphere. And its source is the sun itself, as you can see in this image where the wind is blowing radially outward. So this is SOHO data. Which is data taken from a spacecraft that's fixed in Earth orbit near the Earth. So what you're seeing is the streaming outward toward the interstellar space. So what we know is out there is a huge comet-like shaped object. Here's the sun. Here are the orbits of the planets which orbit the sun, as you can see. This was the trajectory of Voyager 1, which was deflected upward out of the plane of the planets when it flew by Saturn, and it's heading upward at about 35 degrees at latitude. Following along behind a few years was Voyager 2, which stayed in the plane so it could do, this was flying by Saturn, so that we didn't do that. We didn't fly by Saturn for deflection. We just used it to fling ourselves further out. But at Neptune, Voyager 2 was positioned to fly over the North Pole of Neptune, and so it was deflected downward toward the southern region. So we have one sample of what this bubble looks like that the sun creates around itself. That wind I showed you, that streaming from the sun creates this huge bubble. And the bubble we measured the bubble going up north and down south. At some point, that bubble keeps expanding until it can no longer push against what's out, because the density falls off, and it meets the interstellar wind and forms a kind of a surface which bounds and separates interstellar material coming from this direction with solar material coming outward, streaming outward, creating this bubble-like feature. But it has a tail because the wind here can't keep pushing. It has to turn around and go down the tail of a comet-shaped magnetic field. So that's what's out there, and what we've And what it creates is these kinds of shock waves. So this is a star, and this is the wind coming from that star. It's supersonic wind, so in fact it forms a shock up here, and now here is interstellar space. Behind this region, we are right near the Earth. We're seeing, of course, the expansion of the corona of the sun. Out here, we're seeing the interface between solar material, which creates this shock wave, and interstellar material, which is coming from this direction, pushing against the solar material and creating this bubble-like with a long tail. This is a real image taken by other spacecraft, Hubble spacecraft, a telescope image. So you can see the interaction between the interstellar wind, that is the wind of stuff coming from other stars, and our heliosphere, which is inside. So this is the star. There's a wind coming from that star, just like the one we have coming from our sun, and that wind has to turn and move downward because it runs into this shock wave that you can see here. You can see this in your kitchen sink. So you should, when you get home, take a look. This is a model of what's actually going on out there. This is the water coming out of a tap. This is the kitchen sink. You can see the water is very fast. It hits the bottom of the sink. It streams radially outward in all directions, but not equally because the pressures are not the same and outside pushing back. But you can see the water is very thin and very fast. The water here is moving faster than the speed of waves, and so but it's getting thinner and thinner as it spreads out, and eventually can't keep pushing out against what's outside, and it abruptly slows down in a shock and then turns and goes down the drain. So all of this water you see going down the drain is water that's come from all directions, but it's all funneled down the drain. And this is the supersonic wind. It's moving faster than the waves in the wind. But it's getting thinner and thinner, and at some point it abruptly slows down and turns. And that's what we have done with Voyager 1. Voyager 1 is first one to have left the bubble and entered interstellar space, which is what's out here. And this is the water, of course, in the kitchen sink. We don't have a picture like this of what's going on with our own solar system, but it gives you an idea of what the sun is doing. It has this very fast flow of solar wind material pushing outward against what's outside, but that balances by pressure outside at some distance from the sun. So the sun's there, and all the planets are way in here because this feature is much further out than any of the planets. And I'll show you what we've discovered about in the solar system, where this feature happens. There we go. So this is the picture of what we think is going on. That the sun is a source of material coming out at 400 kilometers per second, a million miles per hour, creating this huge bubble around itself, and a bubble with a tail. So here's the sun, here are the planets, then here's the supersonic part of the flow of the wind that abruptly slows down in a sonic boom, if you like, and then it turns and goes down the tail and forms a long comet-like tail. So that's what I just showed you in the kitchen sink, is same things going on in the kitchen sink. And outside, once the wind leaves the heliosphere, it will slow down and has to affect that what's outside is the interstellar wind has to flow around the outside of this object. So we have solar wind coming out, balancing interstellar wind coming in, and there's a boundary between them which separates what's outside from what's inside that came from the sun. Both spacecraft are now outside of this bubble. Voyager 1 left the bubble in 2012, and Voyager 2 left the bubble just last year. It was a slower spacecraft, so it took longer to get out. But both are now in interstellar space, where the wind from other stars is coming from this direction and is deflected around the bubble created by the sun. So this is from the sun, And this is from stars, from other stars nearby, which has come of some great distance to interact with our solar system. So this is a kind of a cartoon sketch of what's happening when that wind finally gets out to the edge of things. So here's the deflection at Voyager 1 and Voyager 2 were deflected upward by their flyby of the planets. As they headed out there, there's a wind that's outside the heliosphere that's ionized, it's charged. It can't get in easily, and so that there's a boundary layer of material that comes in, that does diffused in, and we've been measuring that, and at some point it will, once we find this boundary, which is called the heliopause, once we cross the boundary, it will suddenly be much denser, as represented by the extra dots you see in this cartoon. So these are the interstellar particles trying to get in, and you can see some of them do get through, and this is the solar wind which keeps pushing them back out. All right, so this is a measure of the counting rate of cosmic rays, which are the ionized particles outside trying to get in. They're created by supernovae, nearby supernovae, and they flow toward the Earth, and just as in that cartoon. So this is a plot as a function of time of the counting rate of these cosmic rays, which are outside the bubble, leaking in, diffusing in. So back in 1977, when we first launched, that's the counting rate of these particles coming in from the galaxy, the cosmic ray particles. And that's 1977 when we were launched. And as time went on, as we moved further out, actually the density or the number of these things actually got smaller. We were moving away from the source, and the intensity was getting smaller. That's because the solar activity kept pushing it back out faster than it was coming in. And there's an 11-year cycle, so we were right at the part of the cycle where the solar wind was beginning to sweep them out faster than they came in. And you can see suddenly the intensity went down from what we measured. Fewer could get in because the wind outward was stronger. And then the solar activity died down, and the particles came back, but they still weren't as intense as they were at launch. And so you can see that as the sun goes through its 11-year cycle of solar activity, when there's a lot of solar activity, it's very effective at sweeping out the ions which leak in. But when the solar activity is low, the particles from outside can sweep in. And you can see this was 1980, 30 AU. 1 AU is the distance of the sun to the Earth. 30 AU is where Neptune is. You can see that the intensity of these particles from outside was actually larger than it was at Earth when we launched. But then this is an 11-year solar cycle of activity, and it dropped again. And by 1995, it was twice as far out as it had been for when it left Neptune, and so it was only a little bit less, a little extra compared to what it had been in about 1990. Here's 90 AU in 2003, still another gradual increase in these particles from outside getting in. They're called the cosmic rays, and they can flow in against the outward expanding solar wind. And there we are at 120 AU with the spacecraft. Neptune's at 30. This is 4 times as far from the sun as Neptune is. And you can see the counting rate was getting quite large. And then on 2012, August 25th, it jumped up to an intensity which is what's outside the bubble. These are the cosmic ray particles outside the bubble, which came from the explosion of other stars millions of years ago. And we saw them for the first time back in 2012. We now know that the size of the bubble that we're in is about 120 astronomical units in radius. That is, Neptune's at 30, so it's 4 times the radius of this bubble is 4 times the orbit of Neptune. And we're now outside, as shown by these 2 small Voyager spacecraft, which of course are grossly enlarged on the scale of the heliosphere. They're tiny little objects measuring the solar wind in the wind in interstellar space, there's a wind coming from this direction, and there's this bubble or heliosphere which deflects the wind around it like this, and there's a kind of a shock wave that sets up in front of it. Voyager 1 is entered that, was out here in 2012, and at last year, 2018, the Voyager 2 also entered this region, became interstellar spacecraft in November of last year. So both spacecraft are like this drawing, which outside in interstellar space, pushing against what's out there, creating this bubble around the Earth, which varies with the solar activity in terms of how size and how effective it is for particles coming in. And we are now, both spacecraft are on their way out, or outside, and they're on their way further away from the sun. But the intensity outside doesn't depend very much on where the sun is. Once you get out in interstellar space, you're mainly seeing particles that have come from other supernovae many years ago. So there's where Voyager is in a reconstruction of the galaxy. Here's where it is. You can see that there are these rings which form, spiral arms that form. Voyager 2 is here. This is a plate which is a gold-coated record. This is a cover. You don't see the record. The record is a standard 33, well, it's actually 16 2/3 RPM record, which has on it images of Earth and other records of Earth, which, should this ever be found, and I think it's unlikely it will ever be found, it's really more a message to those of us here on Earth that we could send such a signal. We could send the signal out to the Milky Way, into the Milky Way galaxy, saying there is this place where these came from, and it would be up to the finder to figure out where that was. But they're being given the clues by the location of where we are compared to the stars, which they would, whoever they are, and I think they're not likely, but whoever they would be be able to say where the spacecraft was in interstellar space, where these cosmic rays came from. So that's the story. We're waiting. We have about probably 5 years more of power, 5 more years of being able to run the spacecraft, and so by that time we're still moving outward at several 3 AU per year, 3 astronomical units per year. So each year we get that much further from the sun, but we'll still be very close. And the spacecraft will both end up being in interstellar space between the stars, basically for billions of years. And should there be anything out there that could find it, maybe someday it will be found. But I think that's really not the point. The real point is that we actually finally developed the technology to launch this into interstellar space from Earth. And we are now tracking it as long as we have power from the transmitter, which is probably another 3 or 4 or 5 years. And then they will be silent ambassadors to the Milky Way galaxy. Thank you very much.
Thank you, Professor Stone, for your very insightful and inspiring lecture. I'm pretty sure all of us have learned so much today. And can you please stay right now, because this will be our question and answer section.
Thank you very much, Professor Stone, for your fascinating talk. I think we've all learnt a lot about Voyager and about the planets that are around us and our position in the solar system. I'm sure that there are a lot of questions that people are burning to ask. I hope they are.
So in one of the slides, you showed the number of instruments that was brought onto Voyager. So I'm curious, when you were designing the actual aircraft, it was a one, you have one shot. So I'm assuming that for every instrument that made it onto the craft, many instruments were left out. So I'm curious, what type of decisions went into deciding, what to go on and what to leave out? Presumably, you faced some budget, right? What you can bring.
Yes, yeah. Normally the process is, first of all, there's a study which recommends what the key measurements are, and then there's a competition that is open to the science community to develop instruments to address the key uncertainties or unknowns about what's out there. And so you want to measure magnetic field, you want to measure the solar wind, you want to measure the interstellar wind. You have a list of such things the community has agreed are the key factors in understanding the system, and then you invite proposals for instruments to make those measurements. And of course, as time goes on, you can do more and more sophisticated measurements because all of our electronics capability is much larger today than it was many years ago when these instruments were built. These were built in the early 70s, and today they're really primitive, but in fact, that's just the nature of the problem. It just takes a long time to get out there.
Thank you so much, Dr. Stone, for doing the talk and coming to Hong Kong. We really appreciate it. My question is actually still related to the instruments. As the Voyagers are going to carry on and their energy sources are going to be depleted, which instrument will be the last instrument that will be functioning before we actually switch it off?
Well, assuming nothing breaks, the ordering has been determined, and it's we have two spacecrafts, so we've tried to balance things. But the cosmic ray instrument is the first one that we have now has only just the power it takes. It has no extra, we don't have any extra power left. And that will be the first one that will be turned off in a year or so. Well, it'll be turned off after we've turned off all the backup instruments. So we have 5 instruments, and on Voyager 1, all 5 are working. But the first thing we'll do, we will turn off some heaters and let them get colder. And after we've done that for all 5 instruments, then we'll turn off instruments. So we have started turning off instruments to make them colder, and we turned off the cosmic ray instrument on Voyager 2 in order to have enough power for everything else. But we've turned off the heater, and so it got very cold, but it still works. So the only thing left after we turned off the rest of the heaters on the other instruments is we'll have to turn that instrument off. And so we've got a stepwise process, and we have 2 spacecrafts, so we can make sure we try to make sure we have one of each rather than we have 2 right now, but we'll have to turn off one of the solar wind, one of the cosmic ray instruments on one, and some other instrument on number 2. So that's the strategy we have, and it'll take about 5 years to turn off all the heaters and have to start turning off the instruments.
If you have a chance to do it again, what would you do differently?
Well, I think given what we could do at the time, this is probably about what you would do. We can now do much better, obviously. The instrumentation was designed in the 1970s. The amount of memory we have only, I think 4,000 words of memory. That's nothing compared to what you can do today. So for the later missions like Galileo and Cassini, which you may have seen some slides of when I showed them, are much more advanced in terms of computing power and so on. But they're not going out. They were both dumped into Jupiter and Saturn. So there will be future missions, but most of them will stay in orbit around a planet. We do have working groups looking at, well, what would the next step look like on interstellar? It takes a long time to get out there, and it's hard to go much faster than Voyager. We can do somewhat faster. So eventually there'll be a decision, but right now most of the missions want to go back to a planet and not just off into interstellar space.
I want to just first congratulate the success of the project, because it's the image taken for Voyager. It's become textbook image for the generations that inspire all the young people for many of us. And I just want to ask you personally, what are your most memorable parts of the mission? I know there are many challenges, and what is the most challenging thing that you face in?
Well, I think what we learned is that there's a lot out there to be discovered. So it's hard to pick one thing. But if I had to pick one thing, it would be the level of volcanic activity on Io. I mean, before that, there were no volcanoes anywhere else in the solar system we knew of. We just here on Earth. And it turned out this little tiny moon has a large volcanic activity to it, and it makes it's so. But that's just the first example of many that we began to see up close. That in fact our models of the solar system were just much too elementary. But that's because we didn't have much data to base it on. And Voyager really opened up. Now we've had Galileo go back to Jupiter and really take the next step of spending a lot of time on Jupiter. And we had the Cassini Spacecraft, which went back and spent its time in Saturn 10 years or so. And of course, that's another big step. But it was all predicated on the fact that Voyager revealed how complicated and how diverse bodies are in the solar system.
First off, I'd like to thank you for this great lecture. And I'm really fascinated by how you're able to communicate with the Voyager from such a distance. Without the issue of the power, how far into interstellar space do you think you could communicate with the Voyager?
Well, you can continue to turn down the bit rate, so that lets you go further. But we decided we'll run out of power to do that in about 5 years. About 5 years is about all the. And then after that, we won't have a power to have any science instruments on.
Were you able to determine much about the chemical composition of the worlds as a function of distance? And I'm particularly interested in how much Uranus and Neptune appeared to be different, given their similar size and mass.
You know, I really not kept up on the detailed differences between the two, but I think Uranus and Neptune are different, partly because Uranus is tipped on its side with its polar axis pointing at the sun for 22 years roughly, and then it goes like this, parallel to the sun. So there are detailed things like that which are clearly different, and which the subsequent missions, which are orbiters, provide a lot more data to do those studies.
So for young people in this room who might have a dream to launch a mission as successful as Voyager, what would be your advice to them? Thank you.
What advice? That's a good question. I think that the opportunity is to study the atmospheres of the planets, to see, and in particular, the atmospheres of Jupiter, Saturn, Uranus, and Neptune, because that's the most accessible sample we have of what's out there. So, I think there's plenty of opportunity for discovery left. This is a stepwise activity, and we can have a lot more, much better instruments today than we had some 30, 40 years ago now.
There's something left out, Pluto. So could you comment on the new Horizons Spacecraft and compare that with the Voyager?
Well, that was the new Horizons Spacecraft that flew by Pluto, and what it found was a very active object again. It was not a surprise for those of us who have seen all what happens at the other planets. It's very cold out there, but even so, there's clearly enough thermal activity to modify the surface. It's not an ancient cratered surface. It's a surface which has clearly had heating events since its formation, and that's not a surprise. It's the details which are unique to Pluto, which make it interesting.
Thank you very much, Dr. Stone, again, for coming and giving this lecture and sharing your insights with us. I was wondering if you can talk about the team dynamics of a project as large as this, and I wonder if you can give us any advice if we're going to do any team-based research operations. What do you think are the main ingredients to make a project like this
I'm
work?
sorry, what's the question? I don't understand the question.
So can you comment on the team, the people who work together on this,
Yes.
and what do you think are most important in making something like this work very well?
Well, I mean, what we did, I can tell you what we did, and what we organized. There were 11 scientific teams, each of which had one of the instruments, and my job, if you like, as the chief scientist, is to coordinate all those to make the best use of the data that we can get back. And I think it's clear that you need that kind of an opportunity because you're in a discovery mode. So some of it you go back because you don't know something, but other things you have models which you want to check. And time goes on. I mean, the science we have today is much more advanced, partly because of Voyager, than it was when Voyager first flew. So it's like all sciences. It's this progress that's important. And the challenge we have is that there's going to be one mission like this a decade that are something like Voyager. And Galileo, Cassini, each took more than a decade to go. So you have to try to pick instruments which address what you know at the time. And usually what we find out is, well, part of what we knew was okay, but there was something else we just didn't understand, and now we understand. If you put different instruments on, you may discover that some of your assumptions were really maybe too primitive for what's really out there. But it's a very complicated process, and it takes on the order of 10 years per cycle for these deep space missions.
Hi, Dr. Stone. Thanks for other than this fabulous science the Voyagers have done. It also inspire a whole generation of students who are interested in space. As I have the privilege to talk to you in the interview 2 days ago, it is the Voyager that inspired me, my interest into astronomy in the 70s. And I would more than happy to let you know that today, by accident, that the inspiration work still carry on today, as we have another 10 students here listening to your talk. And incidentally, it's interesting that we are from the same school, Puching Middle School. To me, it's kind of interesting. My question is that with the recent discovery of the second interstellar object, comet C2019Q4, having an eccentricity so big that it has been from outer space. I know that it may not be a fair question because in science we need more data, but I still cannot keep asking, what's your opinion about that? We have more, observing more interstellar objects. Is it just an observation bias due to our better observation skill, or are there maybe other meaning that you just want to have your opinion?
Yeah, I'm afraid I'm really not up to date on that, so I can't really give you an informed answer. But you're right, you have to continue to look for opportunities and build on what you know. And usually what we find is when we have new kinds of observations, that they will tend to change what you thought was the situation. Sometimes it means you were pretty well right. Other times it means we didn't have all the key facts, and we did the best we had in terms of interpretation. But the data itself is really important, and that's where you want to look at what new measurements can you use to advance the overall knowledge.
Okay, I think it's been a great question and answer session. Thank you very much. Let's have one more opportunity to thank Professor Stone.
Please stay for the souvenir presentation. And let's also take a group photo. Thank you very much. The Shaw Prize lecture is now concluded. I would like to thank you all once again for coming today. Please join our speakers at the reception outside the hall and have a nice day.